welcome to the deep dive.
Mhm.
If you're building AI today, you are intimately familiar with the deployment wall.
Oh, yeah, absolutely.
I mean, you train this massive parameter model, it achieves state-of-the-art results on static benchmarks. But the second you deploy it into an open-ended, non-stationary environment where it actually has to query live APIs, parse messy data, adjust logic on the fly, the whole system just completely freezes.
Right, or just hallucinates wildly.
Exactly. The static sequence prediction paradigm, where an input maps to an output in a single forward pass, it just breaks down when you introduce dynamic execution.
It really does, which is why we're seeing this massive architectural shift across the field right now. We are moving away from just optimizing standard language models toward engineering autonomous, self-correcting reasoning agents.
Yeah, and that brings us to the source material for today's deep dive. We are looking at a really comprehensive, multi-institutional survey paper. It's titled Agentic Reasoning for Large Language Models.
It's a fantastic paper.
Yeah, it's basically a definitive state-of-the-field document. It's co-authored by researchers from UIUC, Meta, Amazon, DeepMind, UCSD, and Yale.
And it's really a critical synthesis of where the engineering is actually heading. The authors take this incredibly dense field and systematically structure it into a clear, three-layered framework.
Right.
You've got the foundational capabilities of a single agent, then the self-evolving adaptation across multiple episodes, and finally, collective multi-agent reasoning. And they look at all of this across both inference time orchestration and post-training optimization regimes.
Okay, let's unpack this, because we really need to deconstruct how this paper mathematically formalizes agentic reasoning.
Yeah, the math is key here.
The foundational premise is just a complete shift away from viewing language modeling as pure sequence prediction. They're framing it entirely through the lens of control theory.
And that shift, honestly, is the fundamental unlock. To formalize a reasoning agent, the authors model the deployment environment as a partially observable Markov decision process, or a POMDP.
Right, a POMDP.
Structurally, this acknowledges that the agent never actually has complete access to the true latent state of its environment.
Right, the state X is hidden.
Exactly. It has to rely on a highly limited observation space, O. So things like the specific text returned by a web search, or a JSON error code from an API, or just a user query.
And within that POMDP framework, the most significant divergence from standard reinforcement learning is really how the policy itself is factorized.
Yeah, this is where it gets really elegant.
Because standard RL, it maps a state or a history directly to an external action. But here, the policy is explicitly decoupled into two distinct probabilities. You have an internal reasoning trace space, which is Z, and an external action space, A.
Right. The agent computes in the reasoning space Z before it ever commits to an irreversible external action in A.
Which makes sense.
The authors literally define the total policy as the product of a reasoning policy generating internal thoughts based on the history and an execution policy, which takes an action based on both the history and that new internal reasoning trace. So by mathematically separating the thinking from the acting, you totally isolate the cognitive load.
But look, if you look at this formulation from a pure optimization standpoint, a really glaring bottleneck emerges pretty quickly.
Oh, for sure. Optimization is the hard part.
Right. Because if the latent environment state X is unobservable, and the reasoning trace Z is purely internal to the model's context window, how do we efficiently optimize that internal reasoning policy?
It's a huge challenge.
Standard reinforcement learning applied here would almost certainly fall into the trap of sparse rewards and extreme variance. I mean, you're trying to optimize internal latent steps based on a heavily delayed external environmental reward.
Yeah, that is the exact optimization bottleneck the entire field has been wrestling with. And the paper addresses it by delineating two complementary regimes to solve this.
Let's get into those.
So the first is in-context reasoning. This is where the model parameters remain completely frozen. You aren't updating weights at all. Instead, the system optimizes the reasoning trajectory by performing an inference time search over that Z space. You see this materialized in methods like Monte Carlo tree search applied to tree of thoughts.
Right, MCTS.
Exactly. The system generates multiple candidate reasoning paths, evaluates them using a heuristic value function, or like a self-reflection prompt, and then selects the path with the highest expected reward before it ever takes an external action.
And the second regime.
The second is post-training reasoning. This is where we actually update the model parameters via RL to align that internal reasoning policy with long-horizon environmental rewards. So instead of relying purely on expensive inference time search, The model basically internalizes the ability to generate high-value reasoning trajectories inherently.
Right. But because that internal reasoning policy still needs to interact with external environments to gather its observation space, the agent requires some really robust core primitives to bridge those internal and external states.
It does. It can't just think in a vacuum.
Exactly. And the authors categorize these into three foundational capabilities. You've got planning, tool use, and search.
Yeah, and planning really serves as the structural constraint there. Instead of naive, open-ended autoregressive generation, which just drifts, robust agents employ structured process formalization.
Right.
The paper highlights that advanced agents encode plans using strict code-like artifacts, or by utilizing frameworks like PDDL, the Planning Domain Definition Language.
Which forces strict compositionality.
Exactly. It ensures the reasoning trace can interface cleanly with classical execution controllers.
And when we look at the search primitive, we are seeing a massive departure from how standard architectures handle information retrieval.
Oh, completely.
I mean, traditional R-read retrieval augmented generation is just a static pre-generation step. You retrieve a document, prepend it to the context window, and generate. But in the systems analyzed here, like Agent G, retrieval is a dynamic, reasoning-driven tool invocation.
They refer to it as agentic RAG.
Right. The agent actively queries a knowledge graph, evaluates the returned observation, and algorithmically decides whether the info is sufficient to proceed or if it needs to, expand the search topology further.
It's iterative. It's thinking about what it found.
Yeah. And here is where the architecture gets highly specific. When researchers move to actually internalize these foundational skills into the model's weights during that post-training optimization regime, we're seeing a really strong convergence on specific algorithms.
Yes. The paper extensively details GRPO, Group Relative Policy Optimization.
Right. Which is everywhere right now.
It has become the standard for reasoning models.
Yeah.
You see it heavily utilized in systems like DeepSeek R1 and Search R1.
Because of the memory efficiency.
Precisely. GRPO is a highly efficient optimization over standard PPO proximal policy optimization because it completely eliminates the need for a separate value network.
Which is huge. In standard PPO, you have an actor network generating the policy and a critic network estimating the baseline value to compute the advantage. That requires massive memory overhead.
Right. Deploying two giant models is a nightmare. But GRPO computes advantages relative to a group of outputs sampled from the exact same prompt, using just the policy model itself.
Mechanistically, the way they define the objective function for GRPO is fascinating. It samples a group of candidate outputs for a single prompt. Then it computes the advantage for each specific output by taking its reward, subtracting the mean reward of the entire group, and then dividing that by the standard deviation of the group's rewards.
It's purely group normalized.
Yeah. Then it optimizes the policy using a clipped surrogate objective, just like PPO, but it subtracts a Kullback-Leibler divergence penalty at the token level.
And that KL divergence penalty is absolutely critical. It acts as a strict mathematical constraint to prevent the updated policy from drifting too far from the original reference model.
Otherwise, it collapses.
Exactly. Without it, the model could easily collapse its probability distribution or just unlearn fundamental language capabilities while it heavily over-optimizes for the reward signal in the reasoning trace.
But let me push back on the core mechanism of GRPO for a second.
Sure.
If it fundamentally relies on a group relative reward, meaning the advantage is strictly normalized against the other samples in that specific batch, doesn't that fundamentally limit the model's ability to evaluate absolute correctness?
How do you mean?
Think about highly deterministic mathematical domains. What happens if every single sample in the group of outputs is factually wrong, but one just happens to be mathematically closer to the answer, or maybe it's simply formatted better?
I see.
If there is no absolute value baseline from a critic network, wouldn't the model still apply a positive advantage to a failed reasoning trace, simply because it was the best of a bad batch?
It's a great question. And from a pure algorithmic standpoint, your concern is entirely valid. A purely relative advantage can absolutely lead to local optima if the baseline is consistently poor.
Right.
However, in practice, GRPO is virtually always deployed alongside highly verifiable rule-based feedback environments. The reward signal itself acts as a strict absolute guardrail. So in deterministic domains, like math or code generation, if all outputs in a sampled group fail a deterministic unit test or a symbolic check, the base rewards assigned to the entire group are uniformly zero.
Oh, I see. So the variance collapses.
Exactly. When the base rewards are uniformly 0, the standard deviation approaches 0, and the group normalized advantage just flattens out entirely.
That makes perfect sense.
It effectively nullifies the policy update for that specific batch, which totally prevents the system from assigning a positive advantage to a failed output. The relative advantage simply accelerates the gradient step when there is actual variance in success within the group. The strictness of the environment's reward function anchors the relative optimization.
That clarifies the mechanics significantly. The verifiable feedback prevents the relative optimization from just drifting into hallucination.
Yeah, you need the strict environment.
So now, foundational agents using these primitives can optimize a reasoning trajectory within a single episode. But real-world deployment environments are highly non-stationary.
They change constantly.
Right. If an agent fails a task, we cannot afford for it to repeat that exact same failure state in the next episode. The system has to optimize its behavior across episodes. Which brings us to the second layer of the paper's framework, self-evolving agents and the meta-learning loop.
The authors formalize this cross-episodic evolution with a very specific meta-update rule. The system maintains an evolvable state, let's call it S, which is updated based on the trajectory of the previous episode and the environmental feedback received.
So S sub k plus 1 is a function of S sub k, the trajectory tau sub k, and feedback F sub k.
Precisely. The crucial distinction here is what actually constitutes that evolvable state S, and the paper categorizes this into 3 distinct typologies.
Right. The first typology is verbal evolution. We see this in architectures like reflection.
Yes, reflection is a classic example.
The evolvable state there is basically just a text-based memory buffer. When the agent fails, it synthesizes its execution error logs into linguistic cues. It generates a natural language reflection outlining why the failure occurred and stores it.
And then in the next episode, that reflection is just injected directly into the context window to constrain the reasoning trace and avoid repeating the error.
Exactly. And then the second typology is procedural evolution, where the state consists of executable artifacts rather than just natural language.
The Voyager system is the prime example here.
Right, Voyager playing Minecraft.
Yeah, it interacts with an environment, it writes Python code to achieve a specific goal, and it relies on an execution engine to verify it. Once verified, the agent stores that successful code function in a vector database.
So it permanently expands its external action space across episodes.
Exactly. It isn't just remembering how to solve a problem verbally. It is physically writing and compiling a new tool to automate the solution moving forward.
And the third typology, structural evolution. That one fundamentally alters the control flow itself.
It's easily the most advanced of the 3.
Yeah. Systems utilizing frameworks like AlphaVolve. They treat the agent's underlying execution architecture like the actual Python scripts, governing how it thinks and plans as the evolvable state.
They utilize an LLM as a mutation operator.
Which is wild. The system analyzes its own performance, proposes structural changes to its own codebase, tests the new architecture, and iteratively rewrites its own logic.
It is essentially applying genetic programming principles, but using an LLM to intelligently guide the mutation step instead of random mutation.
Now, to support any of these self-evolving typologies, the agent obviously must possess highly structured agentic memory. You can't just have a massive text file.
No, flat contextual memory buffers completely fail at scale. The paper details a necessary transition to modular structured memory architectures.
Like MIX.
Yeah, the MIRX framework is a great example. It utilizes semantic decomposition. It actively routes episodic experiences and procedural knowledge to highly specific management modules rather than just dumping everything into a single text document.
And there's also LegoMem, right?
Right. LegoMem ties memory units directly to subtask execution. So it only loads the memory blocks that are strictly relevant to the current operational node the agent is at.
But the mechanics of maintaining this explicit memory state introduce a really massive risk of context window pollution.
Catastrophic forgetting is a huge issue.
Yeah, I mean, if an agent is iteratively appending reflections, compiling new procedural tools, and storing complex structural permutations across hundreds of episodes, all without actually updating the underlying neural network weights, how do these systems prevent the noise from eventually outweighing the signal?
It's the bottleneck.
Right. In a long-horizon deployment, the sheer volume of appended heuristics would inevitably degrade the attention mechanism's ability to focus on the immediate observation space.
That is the defining bottleneck of long-term autonomy. If you just naively append data, the system collapses under its own context weight.
So how do they solve it?
The solution, which is detailed extensively in the paper, involves validator-driven feedback and dynamic memory curation. Advanced memory frameworks, such as workflow memory, deploy active asynchronous management mechanism. They continuously compress, verify, and consolidate stored representations. And crucially, if the agent retrieves a stored heuristic or a procedural tool, and the subsequent action results in a failure flagged by the validator, the system triggers an automatic eviction or revision protocol for that specific memory unit.
Oh, wow. So it's an active survival of the fittest mechanic for the memory.
Exactly. It guarantees a high signal-to-noise ratio by constantly pruning bad memory.
So the memory architecture is intrinsically tied to a continuous verification loop. But even with perfectly optimized dynamic memory, we eventually hit the boundary of what a single agent can physically achieve.
Compute is finite. Context windows are finite.
Exactly. As enterprise tasks scale in complexity, spanning multiple domains, massive data sets, parallel execution ascends, the sequential compute constraints of a single self-evolving agent become a hard physical bottleneck.
So you have to distribute the cognitive load.
Yes, which transitions us from single-agent POMDPs to decentralized POMDPs or DPOMDPs. This is the third layer of the framework, collective multi-agent reasoning.
In a DIC-PO-MDP architecture, the joint policy of the entire system is composed of individual specialized sub-policies. The paper outlines a highly formalized role taxonomy for this.
Right.
You deploy manager agents responsible exclusively for task decomposition and routing. You deploy worker agents specialized purely for specific code execution or data retrieval.
And critic agents.
Right. Critic agents strictly constrained to verification and validation, plus memory keeper agents that maintain the global state synchronization across the swarm.
What really stands out in their analysis of multi-agent reinforcement learning is the treatment of the communication protocol itself.
Yeah, C isn't just data transfer here.
Exactly. In a standard distributed system, communication is just an API payload. But in agentic architectures, an external action by one agent, like transmitting a natural language message or a block of code, acts as the direct prompt that triggers the internal reasoning trace space of the receiving agent.
It creates a highly interdependent web of reasoning policies.
Yeah.
And optimizing this requires post-training topology optimization and programmatic prompt constraints.
Like DSPy assertions.
Yeah, the paper discusses frameworks like DSPy assertions specifically in this context. These are hard-coded algorithmic constraints embedded right within the communication layer.
So how does that look in practice?
If a worker agent outputs a reasoning trace that violates a hard assertion, for example, returning a non-integer when an integer is explicitly required, it triggers an automatic backtracking mechanism.
Oh, so the message never even makes it to the next agent.
Right, the message is blocked. The worker agent is forced to revise its internal reasoning trace, utilizing the assertion error log before the system state is allowed to progress.
But deploying these decentralized topologies introduces a really classic multi-agent reinforcement learning challenge that plagues all distributed systems.
The joint credit assignment problem.
Exactly. In a DICA2 or MDP, where agents are communicating via natural language prompts and generating localized reasoning traces, how do you optimize the system mathematically when the final output fails?
It's incredibly difficult.
Right. If the end result is incorrect, how does the optimization algorithm determine which specific agent's internal reasoning trace was the bottleneck? Was the manager's task decomposition flawed, or did the critic agent just fail to catch a hallucination by the worker?
That is incredibly difficult to map back to a specific policy gradient. But the frameworks analyzed in the paper, such as MALT and MARS, tackle this by utilizing centralized training, decentralized execution paradigms.
CTDE.
Right, CTDE. During the centralized training phase, the optimization algorithm has full global access to the expanded trajectory and the internal reasoning traces of all the agents simultaneously.
Oh, okay.
So the system uses outcome-based reinforcement signals mapped to specific, verifiable subtask boundaries. By isolating the environment transition triggered by a specific worker's action and utilizing a centralized critic network that actually sees the global state, the system can compute individual Q values.
Which allows it to assign localized credit or penalty to a specific agent's policy.
Exactly. This stabilizes the cooperative behavior during training, allowing the agents to execute completely decentrally during actual deployment.
The CTDE paradigm is essential for providing that localized gradient signal. Now, having built this theoretical stack from the single-agent POMDP formulation through the post-training optimization of GRPO into the self-evolving loops with dynamic memory, all the way to decentralized multi-agent coordination, we really need to examine how these architectures are actually evaluated in highly technical domains.
Yeah, because theory is great, but the survey dedicates significant space to real-world instantiations, where the margin for error is effectively zero.
The transition from theory to applied domain execution is definitely where these systems face the highest friction. In the domain of scientific discovery, systems like Curie completely discard open-ended text generation.
They have to. The hallucination risk is too high.
Right. They embed rigorous scientific constraints directly into the control flow via inter-agent checks. And similarly, architectures like prot-agents utilize specialized agents. Critic agents parameterize specifically to constrain protein analysis within valid, verifiable physical and chemical bounds.
The reasoning trace is constantly checked against physical simulators.
We see a parallel approach in mathematics and code domains through program space search. The agents are not simply predicting the next token of a mathematical proof in natural language.
No, they are generating candidate mathematical structures and iteratively filtering them through strict numerical and symbolic simulators.
Exactly. And in the healthcare domain, systems like EH-Regent decompose multi-table electronic health record inference. Instead of generating a text summary about a patient's history, the agent synthesizes executable SQL and Python operations that run directly against the database schema.
Which is brilliant because it guarantees factual data retrieval and entirely bypasses the hallucination risk inherent in summarizing tabular data autoregressively.
But evaluating the actual reasoning capability of these systems in complex domains is structurally really difficult. This is a massive point of friction for practitioners.
Evaluation is arguably the hardest part of the pipeline right now.
With these models executing Python code, querying live APIs, navigating complex semantic graphs, how do the benchmarks physically isolate reasoning failures from simple parsing errors or a broken API tool execution?
Right, like if the API is down, is the agent bad at reasoning?
Exactly. If an agent fails a task, how do we systematically determine that the internal reasoning policy failed, rather than the agent just encountering an unexpected syntax error from an external tool?
It requires a strict bifurcation in the evaluation landscape, which the authors detail extensively. To isolate the pure reasoning policy, researchers utilize mechanism-centric benchmarks such as agent bench and tool bench.
Okay.
These environments isolate primitives like search depth and planning logic in highly controlled deterministic sandboxes. In these environments, tool execution is guaranteed to succeed if the syntax is correct.
Which isolates the evaluation to the reasoning trace itself.
Exactly. Conversely, to evaluate deployment readiness, researchers use application-level end-to-end benchmarks like Webarena or ScienceWorld.
Where the noise is real?
Right. They evaluate the joint execution pipeline in the presence of real-world noise, specifically assessing whether the agent's reasoning policy is robust enough to identify, debug, and actually recover from those exact parsing or execution failures.
So as a practitioner looking at the horizon of this field, what does this comprehensive shift actually mean for you? Let's recap the critical mechanics. We've explored the formal paradigm shift from static sequence prediction to interactive agentic reasoning. We deconstructed the latent space POMDP formulation, mathematically decoupling the internal reasoning trace from the external action space.
Right.
We examined how foundational capabilities are internalized using memory-efficient algorithms like GRPO, anchored by verifiable feedback. We mapped the self-evolving meta-learning loops utilizing dynamic, validator-driven memory, and we scaled that up to multi-agent DIC-POMDP architectures optimized through CTDE paradigms.
The overarching takeaway from this entire survey is that achieving state-of-the-art capability no longer relies purely on scaling static parameter counts or training data.
The compute is shifting.
Yeah, the engineering focus must shift heavily toward designing rigorous environmental feedback loops, building dynamic, self-compressing memory structures, and formulating highly specialized, verifiable optimization objectives.
I want to leave you with a final, really provocative thought from the paper section on open problems, latent agentic reasoning.
This is fascinating.
Throughout this deep dive, we have discussed the reasoning trace space Z, which is currently materialized almost entirely as human-readable text, the standard chain of thought. But natural language is inherently bottlenecked and mathematically inefficient for pure computation.
It really is.
Will the next generation of post-trained models abandon human-readable text during the thinking phase entirely? If the internal reasoning trace is fully internalized into continuous latent vectors, we might see multi-agent systems collaborating, prompting, and optimizing entirely at the vector level.
Operating at a speed and computational complexity completely opaque to human observers, yet vastly more capable.
Exactly. Consider how that transforms the fundamental POMDP formulation we started with today. Thank you for joining us on the Deep Dive.